Okay team, this is the second part of the Carnot cycle vid. We just finished talking about the work done during adiabatic expansion, and now we're going to talk about the isothermal processes. Now for the isothermal expansion, things are a little trickier, and I've run out of room on my blackboard, so I think I'm going to erase the steps except for my isothermal expansion. So keep this picture in your head, but I'm gonna have to go to a new chalkboard. So I'll see you guys in just a second. I 100% forgot to not erase the first step, so let's hope editing Maddie can have my back. I got you, boo. With the isothermal stages of the Carnot cycle, we get to simplify our thermodynamics equation by assuming this is an isothermal process, so this change in temperature is 0. And we're left with the change in the heating is equal to pressure times that change in specific volume. So this is where we're going to actually pull in another equation, because I want to relate pressure to specific volume. So far in this Weather 101 series, anytime we've talked about the ideal gas law, we've written it like this. Pressure is equal to density times the ideal gas constant times temperature. But another form of the ideal gas law is this. Pressure times specific volume is equal to that ideal gas constant times temperature. So we could get an expression for pressure as a function of alpha as that specific volume by just dividing alpha over. Now we're gonna plug this expression in for pressure over in our thermo equation. So my dq equals RT times d alpha over alpha. This is the bit where we're actually gonna do a little calculus. So these are in terms of derivatives, the change of this heating, the change in specific volume, and we're going to take an integral to get rid of those derivatives. Now, since in this system, temperature is constant, because this is an isothermal process, and the gas constant is by definition constant, we don't have to integrate these guys, we can pull them out of our integral. So like doing any math, we're gonna do the same thing to both sides. So I'm gonna take the integral of dq, and that's going to equal RT times the integral of d alpha over alpha. Turns out the integral of a derivative is just the thing itself. So Q equals RT times this integral of d alpha over alpha. If you've had calculus before, this should be a familiar form. I happen to know off the top of my head what the integral of a function that looks like this is, and so I'm just gonna write it out, and why it is that way is the subject of a calculus class and not this short video. So we're gonna end up with Q equals gas constant times temperature times the natural log of my final alpha divided by my initial alpha. What this equation is going to tell us is how much energy the gas is able to take on from that warm reservoir in the casing. So if we were to measure the starting height of the piston and the final height of the piston, and then convert that into our alpha, volume of a cylinder isn't super hard to calculate. We could find out exactly how much energy we pulled from that warm reservoir. And for a perfectly efficient Carnot cycle, Carnot engine, that would be the same amount of energy that is redeposited into that temperature reservoir in the casing during isothermal compression. So a typical type of problem you might do with a, say, Carnot cycle would be, hey, if the gas absorbs this much energy and the cylinder the piston is in is this big, how far does the piston move under isothermal expansion? Something like that. All right, team, I think that's it for the Carnot cycle. And then the last section of this first law video is we're going to do a meteorology example problem.
So I will see you guys over at the 6th and final installment of my first law of thermodynamics series. But until then, bye team.